This one we could view similarly. Square root of 6 times square root of 6 for the first. For the outers, minus square root of 6 times square root of 5. For the inners, plus square root of 5 times square root of 6. And for the last, since one's a subtraction and one's an addition, think of a positive and negative, we have square root of 5 times square root of 5. And similar to what we saw in example 1, we can put things back together, and if we have a perfect square underneath, then we get some cancellation. So putting square root of 6 times square root of 6 together as a single square root, 6 times 6, you've got 36, and it's square root of 6. Those square roots, since we have real numbers and we're multiplying the same thing, the squaring is canceling out the square root. In the middle, yes, we can find out that that's going to be square root of 30, which cannot be simplified, but we're adding the opposite of it here, and it is the same regardless of the order of the multiplication. So that's the middle two are going to cancel out, and we've got the square root of 5 multiplied to itself, i.e. squaring cancels it out. The second option would be to recognize that we're dealing with conjugates of each other. When you're multiplying two binomials that look almost exactly the same, but one of them has addition and the other has subtraction, there's a formula called the difference of squares formula. Our a in this one is square root of 6, and b is square root of 5. And as we saw in some earlier examples, the squaring of the square roots, since we have real numbers there, what's underneath the square roots are non-negative, then we'll get cancellation, and that's 6 minus 5 again. Just a bit quicker when we recognize that a plus b and a minus b are conjugates, and then we could use the difference of squares. Now, the order of the multiplication would not have mattered. It could have been a minus b, that quantity, times the parentheses a plus b. In number 4,